Swayam Prabha. Digital India. Educated India.
Welcome everyone to this NPTEL online certification course on techniques of materials characterization, and we are now in module 10. We are discussing about X-ray diffraction, and this is the second lecture. Until up to now about X-ray diffraction we have discussed in ninth module. Basically that was the first module dedicated to X-ray diffraction. We discussed about the generation of X-ray, how X-rays are generated, what exactly is characteristic radiation, what is continuous spectrum, and how the X-rays is generated when through target when an electron beam is hitting the target metal. All of these aspects we have discussed so far, and in the last class we were continuing that discussion a little further, and we were discussing about the absorption, X-ray absorption. We discussed about the absorption age and so on. And now from this week onwards, this lecture onwards, we will start discussing about the intensity of the diffracted beam. And before that, we will just left one small topic in the X-ray absorption and generation of X-ray and instrumentation of an X-ray tube. That is X-ray filters. So, we will just discuss about that briefly, and then we will start our discussion about the intensity of X-ray beam, intensity of the diffracted beam. And first we will discuss about the Bragg's law revisited from this intensity perspective. We will discuss about why we need to separately discuss the intensity of X-ray diffraction even if we have the Bragg's law. And then we will discuss about X-ray scattering by an electron. And there are two defects basically in X-ray scattering. We will try to discuss about one in this class, and the next one we will discuss another. So, that first effect we will discuss in this class is Thomson scattering. Okay. So, X-ray filter, I think we already discussed about the X-ray absorption, how the absorption happens, true absorption, what happens in a true absorption, and then what the fluorescence radiation and photoelectric generation, all of these things we discussed. So, we know basically what an absorption phenomena is all about, and towards the end we discussed that why we are looking for an absorption, what is the main implication of a characteristic radiation and an absorption. And there one thing was told that the diffraction experiments basically require an X-ray radiation which is as closely monochromatic as possible, because what happens is if you, and that is what the importance of having this characteristic spectrum over the continuous spectrum, because if you look at here, this is the characteristic spectrum, and this is the K alpha line and this is the K beta line. And this K alpha line, we discussed that it is very sharply defined, the lambda value, that wavelength at which this characteristic radiation occurs. It only depends on the atomic number and it does not depend on the voltage, applied voltage, whereas continuous spectrum does depend on applied voltage, short wavelength limit, and then maximum in continuous spectrum. All of these things depends on the wavelength of or the voltage used to accelerate this electrons. But characteristic radiation is what their number one, their wavelength is very well defined, A, and B, they are very narrow. So, the spread of this characteristic spectrums is also very narrow. So, we tend to use such monochromatic beam for any diffraction experiment, because that also we discussed in diffraction experiment you basically need n lambda equals 2d sin theta. So, there is a Bragg's law, and there lambda we want it to be constant, as constant as possible, so that we can keep at least one of this constant. So, there are like 4 variables n, lambda, d and sin theta. So, out of that if we can use a monochromatic beam, at least one of these variables we can keep it constant, and we can then discuss about the rest of the other variables, how to keep them constant and so on. We have seen this when discussing about WDS, we saw how we can vary the lambda and then we can keep the d constant and so on. But for X-ray diffraction, of course, we would like to keep the lambda to be constant, and this is possible when we use a monochromatic radiation. Okay, so that is fine. Now, point is, the monochromatic radiation, in order to generate a monochromatic radiation, let us say I want to generate a K alpha radiation. So, it is, even if it is very fine and very well defined, but we have an instrumentation limitation. So, what happens is, even though I want a K alpha, pure K alpha radiation from my X-ray tube. So, like I want an electron beam is hitting the target metal, and then it is characterized, I am above a critical excitation voltage, everything is fine. I am generating a K alpha, but how I ensure that I am getting, when the X-ray beam is coming out of this X-ray tube, how I will ensure that I am getting a pure X-ray K alpha X-ray. I can obviously use some kind of a beryllium window is there, just to make sure that I cut off most of the other wavelengths. But still, normally what happens when an X-ray tube is operated at a voltage above this critical excitation voltage, not only strong K alpha, but we also have a very weak but significant presence of K beta radiation, and since K alpha and K beta, these are very close wavelengths, okay. That is why it is almost impossible to separate them out in a regular situation, and there will also be a continuous spectrum, which we already discussed, mostly forms the background. So, all these things will be mixed together, K alpha, K beta and the continuous spectrum. Out of all of this, as we understood, K alpha is the most desired one, and the rest of this K beta or the continuous spectrum is undesirable one. Separating continuous spectrum is not that difficult. So, we can use this beryllium window, and we can basically, by absorbing most of the absorption age is such that, for the beryllium window, the absorption is such that it will eat all the other continuous spectrums. And remember one thing, this continuous the absorption, not only the absorption age, but other parts, the absorption coefficient is pretty high, and continuous spectrum, the energy of the continuous spectrum is also pretty low in any other place except for this near to the short wavelength region, the intensity of continuous spectrum is pretty low. So, this beryllium window is quite well to separate out or to filter out the normal continuous spectrum. Now, the only difficulty that we have is how to separate the K beta line or K beta intensity from K alpha intensity, so that K alpha characteristic emission, so that we can get a pure monochromatic beam. So, that is where this X-ray filters, the concept of X-ray filter comes in. So, we can use basically a filter to separate out the K alpha and K beta primarily, of course. So, the filter, and here we will take the advantage of X-ray absorption. We understood that X-ray absorption also is very much specific, it happens at a specific wavelength. So, that also we have seen, and it is related to the characteristic radiation only. So, fluorescence radiation and characteristic radiation is basically the same thing. We discussed about that in the last class. So, if we look at this absorption age, we know that K absorption age is happening over a very fixed wavelength, and the absorption coefficient also increases by many fold in this near this absorption age, and that is quite good enough to sort of stop any kind of X-ray incoming X-ray radiation. If the wavelength is very close to, we have seen this in the last class, if the X-ray the intensity of X-ray wavelength just close to this absorption age is many fold just after this absorption age. So, there is a huge possibility of absorbing the incoming X-ray if I am operating very close to this absorption age wavelength, and that is what we will try to take advantage of. So, we will put a filter. So, we imagine that an X-ray beam is coming out of the X-ray tube, and this has K alpha and K beta radiations mixed. Now, we put a filter, we put a material in the path of that incoming X-ray beam in such a way, and the choice of the material, we make it in such a way that the K absorption age. So, this K absorption age intensity of this material, this lies between the K alpha and K beta line of, or K beta characteristic radiation of the material, target metal in this case. So, target metal is generating a K alpha and K beta, and I am using a filter material in the path of that beam which is coming out of the X-ray tube. which has its K absorption age exactly between the wavelength, I am talking in terms of wavelength, exactly in between this K alpha and K radiation, K beta radiation. Okay. The thumb rule normally for such material, to find out exactly a material. So, I have to basically, for filter, I have to basically find out another metal which has an absorption age at an wavelength between K alpha and K beta of the target metal. So, the thumb rule normally is that close to near atomic number of 30. So, those transition elements, basically they are mostly the transition elements which are typically used as a target metal, copper, cobalt and so on. Thumb rule is that we use the filter material which has one atomic number less than that of the target metal. So, for example, if the target metal has a atomic number of 30, we can use copper, something like that. So, we can use copper with 29. So, if it is, I think the relationship goes, if I am not wrong, yes, it is copper and nickel. So, if nickel is if the target is copper, I can use a nickel filter. The most important example here. So, if I have a copper 29 as the target metal, I will be using a nickel filter 28 atomic number as the filter material. Okay. So, now what happens is, if I think about this, then what this filter material does is, it will absorb the K beta component, because what is happening is, if we can think of this one basically. So, we have the K alpha and K beta radiation coming out of copper, and we have a nickel filter whose absorption age is exactly in between that. So, for K alpha radiation, the absorption, it is before the absorption age, where the absorption coefficient of nickel is pretty low, but right after this absorption age, for K beta line, the absorption coefficient, it is after the absorption age, and this is now pretty high. The absorption age is, or the absorption coefficient is very high for K beta line, whereas for K alpha line, the absorption coefficient of nickel filter is pretty low. So, what will finally happen is that the K alpha radiation of copper can go through almost without much of an absorption, it can go through the nickel filter, but K beta, now because of this absorption age is there, the absorption coefficient of nickel will be sufficiently high to capture the K beta. So, K beta will be absorbed, but K alpha will not. So, filter material, basically they are chosen in such a way that they will selectively absorb certain wavelengths from the incoming X-ray. That is the purpose. That is why it is called a filter material. Okay. So, this example again, as I was talking, we are showing this for a copper target and for a nickel filter, and this is what the initially this is how the spectrum looks like, the characteristic spectrum of copper looks like. K alpha and K beta, they have K beta is quite large as compared to K alpha lines. It's considerable intensity is there for K beta. Now, once I use this filter material, K beta line is almost, K beta characteristic radiation is almost gone. So, I am not getting much of a K beta here. So, this shows the effectiveness of such filtering material, and it takes advantage of the X-ray absorption. Now, we will discuss couple of characteristics of this filter metal. The first thing is, we have seen from this equation, absorption, X-ray absorption equation, is that the absorption of the material or the absorbing power of any material depends not only on its density, definitely it depends on its density, but also on the thickness of this material. So, the thicker this filter, the higher will be the absorption of K beta radiation, and the lower will be the ratio of the intensity of K beta to K alpha in the transmitted beam. So, basically that means that if I use a thick filter, I will be able to absorb K beta much more efficiently, and then in the final beam, the K alpha radiation to K beta radiation, this ratio will be much higher. Okay. The problem in this process is that this filtration is not 100% perfect. What I mean is that even if the absorption coefficient of nickel is pretty low for K alpha, but it is not completely, it cannot be ignored. It is still quite significant to bring down the intensity of the K alpha radiation as well. So, that means the overall intensity of this X-ray beam will come down, both for K alpha and K beta. K beta will almost be cut off, but in the process K alpha radiation or intensity of the K alpha radiation will also be coming down. So, this filtration process is good to give me a K alpha radiation, pure K alpha radiation, but at the same time it will be sort of cutting down the intensity of the K alpha. So, this is sort of a trade off. In the process of suppression of this K beta component, we are weakening the K alpha component. So, that we have to accept that, and depending on this our intended purpose, we have to sort of very reasonably we have to use this filtering material. So, if you take some kind of a example, any reduction in the intensity of K alpha line about half of its original value. So, if the filter material is such that it will reduce the K alpha value by almost half, 50% of K alpha radiation is cut off in the filter, but that will increase the ratio of intensity of K beta by K alpha to about 1/9, which is in the original. So, this is, if you look at this red one is the original line where K beta to K alpha ratio is 1:9. So, for a pretty high amount of K beta is there. From there, after filtering, this radiation, this ratio will become almost like 1:500. So, beta lines is almost completely removed and alpha line is still there at a ratio of 1:500, but what happens in the process is the intensity, the absolute intensity of K alpha light is almost becoming 50% of what it was in the original material. So, but point is, if we in the starting itself, if you start with sufficient intensity for K alpha, so even after the filtering, the K alpha intensity used to be there. You have to make sure there is sufficient amount of K alpha intensity is there, it remains even after filtering, and to ensure that we start with a very high intensity of this K alpha line, and this level 1:500 is generally what is sort of recommended for any kind of diffraction experiment. So, the K beta, the filtering material, the efficiency of the filtering material is chosen in such a way, or the thickness of this filtering material is chosen in such a way that it will be able to sort of bring down the ratio of K beta to K alpha at 1:500. Then this is what the standard or rather I would say X-ray manufacturers, they follow this kind of a standard. Okay. So, now we will just quickly glance through some of these examples of this filter materials, and below this is a table which shows that what are the typical filters that is used for what kind of. So, this is like a combination, filtering material, filter material and the target metal, these two comes in a combination. You cannot just simply arbitrarily use any filter material for any target material. If it is, for example, if it is moly, you have to use something like zirconium. If it is copper, you have to use nickel. If it is cobalt, it is iron, so on and so forth. Now, you can see the efficiency of this filtering material. For example, again we will take the copper nickel example. So, the incident beam has a K alpha, intensity of K alpha versus intensity of K beta, which is around 7.5. Now, if we use something like a nickel filter with a thickness of only 0.008 inch, that is the thickness, very thin nickel filter you use, and this is the kind of density that you use. This is the rho value that you use there in nickel density, and you will be able to now cut down the beta K alpha intensity of K alpha to intensity of K beta. You will be able to maintain it at a ratio of 500:1, which is, as I just now explained, that it is sufficient for any diffraction, and that is the kind of a gold standard for any diffraction experiment. So, only using a nickel filter of this much of thickness, point very thin, and the density of this, you can cut down most of the beta. And if you look at now in the process, if you look at the intensity of the ratio of the K alpha which is transmitted versus the K beta which is incident, this ratio is coming down to be only 0.42. From 7.5 it is coming down to 0.42. So, remember this, that how much, and this tells how much K alpha radiation in the process of suppressing the K beta, how much K alpha radiation is cut down, right. So, here we are taking the K alpha, intensity of K alpha in the transmitted beam versus intensity of K beta in the incident beam, and compared to the incident beam, now most of the K alpha, K beta is gone, most of the K alpha also is sort of absorbed. So, you are suffering a huge amount of decrease in the intensity, but as I said, this is a trade off. So, you have to live with that. Okay. So, we will stop our discussion about this X-ray filter here, and we will start our discussion about the intensities of diffracted beams. Okay. First thing we have to discuss is Bragg's law. As I said, we already discussed about Bragg's law, and we saw that Bragg's law is good enough to tell you exactly when the diffraction phenomena will happen. So, we all know that, okay, fine, this is a Bragg's law, the typical way of defining Bragg's law, n lambda equals 2d sin theta, and we have proved it in geometrically as well. Okay, that if the lambda is such that X-ray intensity is such, and that when it falls on the atomic planes, and this lambda, that wavelength is a basically integral multiple of the path difference, which is defined by 2d sin theta, then there will be an constructive interference, and we should get a considerable, or there will be constructive interference between the X-ray beams which are diffracted, which are scattered, and we should get then considerable intensity. So, this is what we have already seen. Point is, this is half of the story. Okay, there is rest half. How? Basically, what happens is that position of the atoms in the unit cell, that also affect the intensity, X-ray intensity. Okay. Basically, Bragg's law gives you only the direction of the diffracted beam. Which direction? Direction means how the X-ray beam should fall on an atomic plane, and after diffraction, after scattering, in which direction this atomic planes will, or this X-ray beams that is coming out of this atomic planes, in which direction they will have the constructive interference. That is it. So, Bragg's law will tell you only up to that, the direction of the diffracted beam, or the direction in which the constructive interference will happen, basically sin theta. If you know the 2D, that is your material, and lambda, that is your X-ray intensity, then which direction, or which of the atomic planes, in which direction this diffraction should happen, right. It does not talk anything about the intensity of the diffracted beam. So, in those direction, the beam that is finally getting diffracted, the beams which are X-ray beams which are going through this constructive interference, what should be the intensity of that beam? That is another very important question, and that question is directly related to the position of the atoms in the unit cell of any material, right. Basically, we express, we'll come to know that if we derive these conditions of intensity for an unit cell by the basic definition of the unit cell, that it is a repetitive unit, it is the smallest unit which has all the crystallographic information about a material. Just by repeating the unit cell, we can construct the entire material. So, by virtue of that, if we define how the intensities are depending on the atomic positions in a unit cell, basically we can derive for the entire material. That is what. So, this is something that we will be going to discuss, how the position of the atoms in the unit cell are affecting the intensity of the X-ray diffractions, even if Bragg's law is satisfied for them. And this is simply because the arrangements of atoms within an unit cell can eliminate certain diffracted beams completely. You will not, if you do a real diffraction pattern, even if Bragg's law is satisfied for those atomic planes, still you will not be getting any kind of an intensity because of some other kind of consideration. So, intensities, that is why, and those considerations are mostly related to the atomic arrangement in a unit cell. So, that is why what we will be discussing here is basically how this intensity of a diffracted beam depends on the atomic arrangement. Okay. Basically, so this intensity of the diffracted beam is changed by changing this atomic positions. If the atomic positions in unit cell changes, the intensity of the diffracted beam also changes. So, if we measure this intensity of the diffracted beams by back calculation, we can find out the atomic arrangement, we can get an idea about the atomic arrangement within the unit cell. So, that means the determination of crystal structure of a material is not only sufficient if we just go by the Bragg's law, which will tells us that exactly which theta value, which direction I will be getting a diffraction condition satisfied. We also need to measure the intensity of those beams at those 2 theta. That will again tell you the about the atomic arrangement of any material. So, other than this, definitely there are not only atomic arrangement of any material within the unit cell, there are other factors which are also responsible for modifying the intensity of a diffracted beam. There are many other factors which affect the way a crystalline material basically diffract X-ray, and finally, the intensity of the X-ray beam, diffracted beam that is coming out of the material. So, we will go through all of these factors one by one. Most of them, the important ones are mostly related to the crystallography of the material. So, at this point I would assume that people who are doing this course, they have a fairly good amount of knowledge about the crystallography of any material, and if you do not have that, do not worry, please go through any basic book of crystallography, because without crystallography, this part, particularly this part, basically the entire diffraction, if you want to understand, you should have a good knowledge about X-ray, knowledge about the crystallography of material, crystal, the unit cell concept, close packing, and then symmetry and all other concepts. You must have a very good knowledge about that, but particularly this part, the intensity of a diffracted beam. To understand this part, you must have a very good knowledge about crystallography. Without that, it is difficult to understand. Okay. So, we will take a simple example here, how these atomic arrangements are basically influencing the diffracted intensity on and over this Bragg's law. Okay. So, let us imagine these two crystallographic two unit cells here. Now, one is a base centered orthorhombic, another one is a body centered orthorhombic. Base centered orthorhombic means you have, so orthorhombic, I hope it is clear to all. Orthorhombic means it is alpha, beta, gamma, the angle between the directions, all these lattice parameters is 90 degree, but A, B, C, the lattice parameters itself are not same. That is orthorhombic. Okay. So, in this orthorhombic, the base centered one, as it is showing that you have one extra atoms on the bases, and body centered means you have one extra atom in between here. This is the body centered position. Now, if we look at its 1, 0, 0 planes or 0, 0, 1 plane, whatever. If we look at 0, 0, 1 planes, that is this planes, the side planes, all the 6 side planes. Okay. If we look at this, for this base centered one, what we have is all the atoms are lying on this 0, 0, 1 plane. I mean, including this base centered atom at all. So, this may be the position or this distance is different from a base centered and a primitive one, the distance is different, but basically the base centered one is lying on 0, 0, 1 planes, all of them. Fine. So, I have the 0, 0, 1 planes here, 0, 0, 1 planes here, and so on and so forth. Now, Bragg's law, if I look at the Bragg's law for this, I have this diffracted beam from this plane, this set of planes, I have this diffracted beam, and I have another diffracted beam from another set of plane. The condition is basically here the lambda has to be an integral multiple of the path difference, and if it is satisfied, these two will undergo and completely and constructive interference, and let us imagine that that is what is happening. Okay. These two are in, and this is a first order diffraction. So, lambda, this multiple, the path difference is equals to lambda, let us imagine here. Okay. Now, for this one, the body centered orthorhombic cell, the point is you have again 0, 0, 1 plane here, look at there, here you do not have an atom, here you do not, here you have this atom is basically coming off this base centered one, you do not have a base centering here. So, this atom is missing, whatever it is, but still from other atoms you have again the same thing, this X-ray beam coming out of the first plane and X-ray beam coming out of this plane, they are in phase, they are completely in phase. So, they will be diffracting, no problem. The path difference here is exactly lambda. Point is, if you look at this 0, 0, 1 planes, you will have halfway between the 0, 0, 1 planes, you have another set of atoms. This is coming out of this. This is basically like I am seeing from the top. Okay, I am seeing from the top. So, I have this layer, one layer, this another layer, and this I have another set of atomic layers which is in between these two 0, 0, 1 planes. Okay. Now, from what happens is again the beam that is diffracted from here, this will have exactly the path difference is lambda by 2 here. If we geometrically calculate, the path difference of this one is exactly lambda by 2. That means, instead of a constructive interference, this one will cause, this beam will cause a destructive interference with the first layer. Okay. So, I will not get any intensity if I consider only these two beams here. They will not undergo any constructive interference, they will undergo a complete destructive interference. Similarly, there may be another atomic plane after this plane, and that will undergo a destructive interference with this beam coming out of this atomic plane. So, ultimately what will happen is that all of these beams coming out of the 001 planes will nullify each other, will undergo destructive interference, and finally, I will not be getting any intensity out of this 001 planes for body centered orthorhombic, but I will be getting it for base centered orthorhombic. Even if the Bragg's law is satisfied for both of them, just because of the atomic arrangements, I will not be getting any diffracted beam from a particular plane for this one, and I will get for that particular plane, I will be getting a diffracted intensity for this one. So, this is again basically tells you the same story, that Bragg's law is not enough to have a diffracted beam. There is atomic arrangement also plays a role in getting a diffracted intensity. So, we will stop here and we will continue this discussion plus the Thomson's effect in the next class. Thank you.